Welcome to lesson 5. In this lesson we are going to explore the STP port roles and their states. On the previous lesson we have explored the lowest bridge IDs, which consisted of priority and MAC addresses. Let's zoom our topology. We have switch 1, switch 2, switch 3, switch 4 and switch 5. According to the design, the lowest bridge ID has switch 1, which starts with 8001 AABB CC 00 2000. After that, switch 2, which ends with 3000. After that, switch 3, which ends with 4000. And after that, switch 4, which ends with 5000. And the last one is switch 5, which ends with 6000. So the highest number of the bridge ID has switch 5 and the lowest has switch 1. According to our route path selection criteria, the first item which is taken into the consideration is lowest bridge ID. So based on this, we can say that the route bridge should be switch 1. On the route bridge, all other ports should be designated ports. In this case, we can duplicate these two labels and attach it to these two ports. Let's duplicate these two and add them here. These two are also going to be designated ports. Maybe we can reduce their size. Let's delete these ones. Duplicate, put here, duplicate, put here, duplicate, put here. Actually, we better move it more close to the port itself. So the ports which are looking toward the route bridge are called route ports. So let's copy and let's reduce the size of this label. So this should be the route port. Later on we will check from the spanning tree topology. Let's duplicate and put it here, also route port. Let's duplicate this one, and this should be the designated port. Let's duplicate this one, and this also should be designated port. Okay, let's now try to understand the status of these two ports. This bridge has ID of 3000 ending and this one is 4000, so this is the lowest. Most probably this should be designated port. Duplicate. Later on we will check it. If we made a mistake, then we will fix it. And this one should be blocking port or alternate discarding. Let's duplicate this one. What does it mean? The alternate discarding port will become a route port if this link will fail. Okay, let's go next. Let's make it a little bit nicer, like this. So if this one is alternate discarding port, these two ports should be designated ports. If we consider the bridge ID of 4000 and 6000, this should have higher priority, so I think that these are designated port. And we will add designated here and designated here. Okay, this one should also be designated port. Duplicate. Okay, this one should also be designated port. Okay, now we have a situation which port role should be this one. So because this one has the bridge priority of 6000 and this one is 3000, this port should be the root port. So let's take something smaller. Duplicate. So this port should be root. Let's duplicate. And one of these ports should be root, but which one? Why? Because this one has the bridge ID of 4000 and this one has of 5000. And based on this, the lowest bridge ID is this one. Plus the root cost from here to the root is 200, but from here to the root is 300. So one of them should be the root port. According to the design, we have another criteria: lower sender bridge ID, lower sender port ID. So this switch has the same bridge ID for these two ports, and the ports are 00 and 01, 0001. So we should consider this bridge. Sender means port ID. Previously I have stated that the port IDs are generally lower on the lower number of ports, and we will check it later from the spanning tree. I think that E/0 should be the root port. So let's move it to the left. In this case, this port will be the blocking one or the alternate discarding. Let's duplicate it and put it here. Okay, now we have two more ports which we have to decide and judge what will be their functionality. By the way, before moving to that two links, we should specify that this on the right to FTP server and to PC4 should be also designated ports. Let's duplicate and put here that this one is designated. And this one is also designated. Okay, next we have to decide the functionality of these two ports. Based on the bridge ID, the switch 4 has smaller bridge ID, so it's of higher priority. It means that these two ports should be designated forwarding. Let's copy from here, duplicate. Again. Okay, let's update the size manually. So this one should be designated forwarding. Let's duplicate, and this one should also be designated forwarding. Now we have to judge what will be the status of these two ports, E12, E13. Then we go back to the lowest sender port ID. The lowest port ID should be E12. In this case, this port should be designated, and this one should be blocking. E12 should be designated, and E13 should be blocking. But there is one problem, that the switch 5 has the lowest bridge ID. In this case, we cannot have designated on one side and designated on the other side. In this case, both of these ports should be blocking or discarding. Let's duplicate this one. Duplicate. Put it here. Duplicate again. And put it here. Okay, we have completed identifying the planet topology. So based on the design, we have a root here, root here, root here, and root here. Blocking, discarding here, 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 and here. And the rest are the designated forwarding ports. Let's check if this is the reality by logging to the switch 1. Let's close everything. Switch 1. Enable show SP or spanning tree, and we can see that the ports ether 00 is designated, 01 is designated, 02 is designated. All of them are designated as we have specified in our design. Let's open switch 2. Switch 2. Enable show spanning tree. We can see that we have a root port on Ethernet 01, which is this one, and the rest ports are designated. I know that you can see more ports than we physically have in our topology. Physically we have only 4 ports, but switch has 8 ports. The rest 4 ports are being sensed like connected because they are connected to the EVNG, and the switch thinks that it has a connectivity and is sending some data there, most probably the BPDUs, but without any results because it doesn't receive anything back. That's why the port is considered designated. If we want to get rid of those ports in the spanning tree, we can just disable those ports by saying shut down, but we are not going to do it here. So let's analyze the switch tree. Switch tree, enable, show spanning tree. As you can see, all of the ports are designated. Now, one of the ports is root, Ethernet 0/2, like we defined it. And one of the ports is blocking or discarding. It is 1/3, which is this one. And the reason we have specified previously. Okay, let's try to understand the status of switch 4. Switch 4. Enable show spanning tree. And we can see that we have a root port on Ethernet 00, and the rest ports are designated like we specified it. Let's analyze switch 5. Switch 5. Enable show spanning tree. As you can see, we have a root port in the direction of Ethernet 0/0, this one. Alternate blocking port Ethernet 0/1, this one. And alternate blocking on Ethernet 1/2, 1/3, these two. And the rest are designated. So it looks like we have identified our port roles correctly. Next, what we are going to do is to check the root cost. Let's check the root cost for switch 2. switch 2. Switch 2 says the cost to the root is 100. Let's check switch 4. Switch 4 root cost is 200. Why? Because it's 100 here and 100 here. Let's check for switch 5. Switch 5 root cost is also 200. Why? Because 100 here and 100 here. Okay, what will happen if we disable the Ethernet port 00 here? Then the traffic from the switch 4 should go this way, and it will increase the cost of the route from 200 to 300. Let's check. We will say configure terminal, interface E0/0. We will say shutdown, and we will say do show spanning tree. As you can see, all ports shifted to designated and forwarding state. Switch thinks that he is a root. You see, it says this is the root. I am a root. And then switch understand that he is not the root, that there is another root, and the root is this one, which is switch 1. And then we see that the port Ethernet 1/3 becomes alternate blocking, this one. And 1/2 becomes the root port, this one. And the root cost becomes 300. Why 300? Because 100 here, 100 here, and 100 here makes 300. Okay, let's switch back the interface and see what is going on. We will say no shut for the interface E/0. And we will check the spanning tree. You see there is a listening mode on Ethernet 0/0. Still listening, and all other ports are designated. And listening also on 1/0. And then we see that it's learning on Ethernet 0/0, and the rest ports are forwarding. And then we see that the Ethernet 0/0 becomes the root again, and all other ports become designated, and the root cost is 200. And all this procedure takes around 30 seconds. Okay. Now, while repeating the same procedure, let's take a Wireshark packet capture. And let's take a Wireshark packet capture on this port, which is going to become root. We will right-click on the switch and say capture. We will choose port 1/2, this one. We will say open Wireshark. Wireshark is opening. And as you can see, there are some messages going through, which we will analyze later. And we will say shutdown for the Ethernet port. Which one? This one, E0/0. We will say shutdown, and we should start to see some activities on the Wireshark. We see TC plus root, topology change. You see, we have an information topology change notification. Let's see the spanning tree status. It is already activated. Then let's bring the Ethernet port back again, like by saying null shut. The Ethernet 0/0 is up. Let's check the spanning tree. Still on the learning stage. Forwarding. Okay, it looks like the convergence has been finalized. Let's stop it. Let's go through the packets. For example, this one. So we see the status on the packet 5 before the port shutdown. We see that this port has a root identifier of 32,768 with the following MAC address, which ends on 2000, and the extension is 1, which is VLAN 1. The root path cost is 200. Max aging timer, hello timer, and forward delay parameters. Let's look for the next packet that we are interested in for the STP. For example, this one. Root identifier as 5000, which is switch 4. Switch 4, because of the loss of the communication with the root, start to consider itself as a root. Why? Because we are using STP, and STP is slow, and before the convergence is being completed or done, the switch may fall into the condition that he thinks that he is a root. And we can see here that he is thinking that he is a root. Then let's go to some other packets. We receive a packet with topology change notification. It means that all other switch has to recalculate their spanning tree topologies. Then we have another frame which says that the root actually is 2000. The path to it is 200. The bridge identifier, which is sending this information, is 6000 or switch 5. And then let's see what happens in the end. For example, this one or last one. We see that the root identifier is 2000 or switch 1. Our current bridge identifier is 5000. Let's close the Wireshark. Quit without saving. The last thing that we are going to check is the PPDUs on Ethernet 0/3 while we're shutting down the Ethernet 0/0. We'll right click, say capture, and choose 0/3. The capture has been started. We receive some CDP data. We receive some spanning tree data, which says that the root identifier is switch 1. And there are hello packets coming from both switches, like switch 2 and switch 5. So what we are going to do is we are going to open switch 4 configuration. We are still on the Ethernet 0/0 configuration. We are going to shut it down and see what will happen. We can see that the root cost is 200, or yes, now the cost is 0, you see, because the switch 4 starts to think that he is a root. then we see that the cost becomes 300. Why? Because the switch identifies that he is not a root anymore. There is a device with a higher root. The bridge identifier of our system is 5000 and the root is 2000. And it says that the root path cost is 300. Let's see if the spanning tree has finished convergence. Yes, looks like the spanning tree has finalized the convergence. Let's stop the capture. This is the CDP, which we will explore later. And last thing that we can see is that root identifier is switch 1. Bridge identifier is our bridge, which is switch 4 with ending MAC address of 5000. And the cost is 300. Why 300? Because we go from switch 4 to switch 5, from switch 5 to switch 3, and from switch 3 to switch 1, and every path is 100. Because we are using Ethernet 10 megabit per second, I think. We will check it later. Then let's enable back the port. And after we enable back the port, we will have a cost back to 200. But we have already stopped the Wireshark. Let's restart it quick without saving. Capture E03. We can see here cost already shifted to 200. Most probably the convergence is nearly finalized. Show spanning tree. Yes, the convergence is finalized and we are back to our standard topology. Let's stop it. Okay, we haven't explored the port state of backup and disabled. We'll explore it now. Let's go to our pictures. So the root and designated port and alternate port we have explored in this lab. We haven't explored the port role as disabled. A disabled port has no role within the operation of spanning tree. So if we go to any port and make it disabled, it will just get disappeared from the spanning tree. It will not show it. And there is last state called backup. The backup port is an additional switch port on the designated switch with a redundant link to the shared segment. Shared segment is a hub because we don't have hub in our topology, and I haven't seen any hub in my last 10 years experience building Ethernet networks. So most probably you will never see this backup port role. So to shared segment for which the switch is designated, the backup port has the discarding state in the active topology. So most probably you will never see this kind of state in your lifetime. What I also wanted to add as an ending to this lesson is the STP states. So when we have a port which is disabled, it doesn't receive BPDU, bridge protocol data units, those packets which are being communicated between switches to build the STP topology. It doesn't send, it doesn't learn the MAC address, it doesn't receive any data, it doesn't send any data. So the disabled port does nothing. The forwarding port is when it is in designated state or forwarding state, which are the roles for the root ports and designated ports. So the forwarding state receive BPDUs, they send BPDUs, they learn MAC addresses, they receive data, they send data, and the duration state is undefined as long as there is a loop. Then we see a blocking state or the alternate discarding state, which we have analyzed. The blocking state port can receive BPDUs, but it doesn't send. Doesn't learn MAC address, doesn't receive data, doesn't send data. Can receive BPDUs. In our topology, these two ports receive BPDUs from switch 4. This port Ethernet 0/1 receive BPDUs from switch 3. This port Ethernet 1/3 receive BPDUs from switch 2. Next we have a states called listening and learning. These are the states which belong to STP but are not applicable in RSTP. So these states receive BPDU, send BPDU while listening and learning. While listening, they do not learn MAC addresses. It means that they are not updating their CAM table on the switch, but during learning, they do update the CAM table. And while listening and learning, they cannot receive or send data, and it lasts for 15 seconds. The total convergence time for STP is from 30 to 50 seconds. But the convergence times for RSTP, which we'll explore on the next lesson, is from 1 to 3 seconds. So it's much faster. Also here we can see that RSTP doesn't wait 50 seconds for listening or 50 seconds for learning. So it transitions ports almost immediately using its handshake mechanism into the forwarding state. One more thing I wanted to point here is that RSTP alternate port role has a discarding state, but the STP alternate port role has a blocking state. If we have explored the CLI, let's say from switch 4, or let's look from switch 5. Show spanning tree. We see that the STP topology, the roles are alternate, designated, root, and the state is blocking. So we can see that the CISCO is correctly displaying the state as blocking in the STP state. So when we switch it to RSTP, it should show discarding instead of blocking. But we will check, will it show it this way or not on the next lesson. So this is all what I wanted to show you in this lesson. If you have any questions, you can ask them on the comment sections of the video. See you on the next lesson. I highly recommend subscribing to my YouTube channel so that you don't miss any new lessons or setup guides that I release.